So let's just do a quick overview of the intermolecular forces because we've already spoken about some of them. So here, our hydrogen bonds are the strongest type of intermolecular force. There are three that you will have learned about or that you will talk about: hydrogen bonds, dipole-dipole interactions, or permanent dipole-dipole interactions, and our London forces. Hydrogen bonds are the strongest. Now, van der Waals is what I was saying earlier. Van der Waals is actually an umbrella term which includes permanent dipole-dipole interactions and London dispersion forces. Now, London dispersion forces are the weakest, so let's add that in. So these are our strongest type of intermolecular force. These are the weakest type of intermolecular force. Hydrogen bonds are strongest. London dispersion forces are weakest. Now, within our van der Waals umbrella, we can talk about our dipole-dipole interactions and our London forces. And within dipole-dipole interactions, there are actually, again, two kinds. One which you may have spoken about and one which you may not. So these dipole-dipole interactions could either be between two permanent dipoles or between a permanent dipole and an induced dipole in a neighboring molecule. So again, this is why when we're doing chemistry, we have to be so specific with our word use. Do you mean to talk about van der Waals as an umbrella term for all of these other interactions? Or did you mean specifically London forces? What is a London force? We're going to talk about it specifically a little bit more in a second. But the other way you might have heard them described is an instantaneous dipole to an induced dipole. I can't spell instantaneous. Instantaneous to induced dipole-dipole attraction. Think about what those words mean. If it's instantaneous and it's interacting with an induced dipole, what does that mean? With our dipole-dipole interactions in the middle, the one that you probably are more comfortable with talking about is the permanent dipole-dipole interaction. Or when you've been taught it, you might have just been taught about dipole-dipole interactions as an umbrella term. Fine. Just be very careful, like I say, that when you're talking about something, if it doesn't matter, you can just use the term dipole-dipole interactions. But if you're talking about a specific permanent dipole interacting with another permanent dipole, then you need to use the term, you need to call it permanent to permanent. But yes, most of you will have either spoken just about dipole-dipole interactions or about specifically permanent dipole to permanent dipole interactions. Okay, hydrogen bonds are the strongest. What is a hydrogen bond? I'll just add that in super quickly. How do we determine a hydrogen bond? I think we look at it again a tiny bit later in one of the exam questions, but we'll look at it now. What is a hydrogen bond? How do they form? It's the attraction between a... Oh, why have I gone orange? I didn't mean to go orange. To go red. It's the attraction between a delta positive hydrogen, so a partially positively charged hydrogen, and the lone pair on a very electronegative element. The lone pair, LP, lone pair on a very electronegative element. I'm trying to get my spelling right. Negative element, specifically oxygen, nitrogen, or fluorine. If oxygen, nitrogen, or fluorine isn't attached to that hydrogen, that hydrogen won't be delta positive enough. That's when hydrogen bonds form. Okay, so if you've got an oxygen, a nitrogen, or fluorine attached to a hydrogen, that's making it delta positive enough. And oxygen, nitrogen, and fluorine also have lone pairs. Those lone pairs are able to be attracted to a delta positive hydrogen in a neighboring molecule. So those are the key aspects. Okay, cool. Let's keep going. So intermolecular forces, let's think about these London forces. So if you've got a non-polar molecule, by that I mean a molecule which has no polarity across it. So molecules we would class as being non-polar, then they don't have a permanent I'm just going to talk about non-polar molecules. So if they are non-polar, then what interactions can you have between other molecules? We're only going to get London dispersion forces. Oops, didn't mean to press that button. Let's go blue again. London or dispersion forces. Acting. How do they form? Or why do they happen? This is a nice, I have seen exam questions where they ask you to describe how a London force arises. So how does it arise? The constant random movements of electrons. We draw them in electron shells and we draw them in bonds, but the reality is they're moving all over the place. It's just these shapes are where we are most likely to find a pair of electrons, or most likely to find an electron. So the constant random movement of electrons leads to the formation of instantaneous dipoles. These instantaneous dipoles induce dipoles in neighboring molecules. These induce dipoles in. So they cause a dipole to occur in neighboring molecule by attracting or repelling an electron. Molecules by attracting or repelling electrons. And the force of attraction is stronger when you've got more electrons within the molecule. If you've got more electrons, you can have a bigger dipole. You can have a bigger dipole, you can have a greater charge difference. If you've got a greater charge difference, you've got a greater attraction. So the force of attraction is stronger the more electrons they are. So moving down group 7. What's happening? They've got more electrons. More electrons as you go down group 7. Therefore, we're going to have, moving down with more electrons, therefore stronger London forces. No, let's go back a step. No, okay, stronger London forces. What does that mean? That means they therefore require more energy to overcome. And what does that impact? It impacts the melting and boiling point. Higher melting point or boiling point, or boiling point. So the more electrons you've got in a molecule, the greater the dipole can be, and that means the greater the attraction to other molecules can be, and therefore the more energy is required to overcome that attraction, and therefore higher the melting point or boiling point. Just be careful with the words you use. I like to use the phrase stronger or greater, because when we talk about like longer chain molecules, personally, I think you should then say that there are more intermolecular attractions because of the longer molecule. There's more places where you can have an intermolecular attraction, but when you're comparing molecules, it's actually the size of the attraction that can change as well. So just be really careful with word use, be very specific. So the attraction is stronger. You can say greater here as well. That would be fine. How are we doing?